Okay. Okay, so then I think I will start. What I wrote on this side was a problem that we assigned last time, and we'll get back to that towards the end of the lecture today. And here is a short outline of what I want to do today. So maybe I will do a little bit more here, but we'll see. And the two first ones are really things that I talked about last time, but I want to repeat the arguments because they are important. Well, the first is not really an argument. The first is really to give you a first glimpse of these Chern classes. I said the double point formula for surfaces in P4, this was given by a certain Chern class. C2 of the normal bundle is equal to D squared. This was the double point formula. These are the invariant. This gives you invariance, or a relation between the invariants of the surface. So, but I did not explain very much what this is really. So I wanted to spend a few minutes on that. But the good reference for all this, well, the big reference is Fulton's book. But as an introduction, you look at Appendix 1A in Hartshorne. And even the application in this case is example 413. But let me still say a little bit about a couple of elements that goes into this. First is Chern classes. So you have a manifold or a variety, smooth variety X. And then a locally free sheaf or vector bundle on X. When I write it this way, it's really a vector bundle, and otherwise I could think of this as a sheaf on X. Say this as rank R. Vector bundle of rank R. This means that over each point you have a vector space of dimension R. And locally this is trivial. Now, so there, we can associate to this here Chern classes, and they appear the following way. If you think about, so that, let me do that over again. Assume that we are in a very nice situation, best possible situation, and that means that you have plenty. So you have plenty of sections, or if you think of E as a sheaf, that you have plenty of sections into X, into E. So each section is a map of the structure sheaf into E, and say you have plenty of those. So say you have this was R, and you have now M here, M sections here, with some M less than or equal to R. Then you can look at the set of points, the locus of points X in X, such that this map here, I mean, you look at over that point, this map here gives you a subvector space of E, and so this subvector space is going to have rank some number less than or equal to m. So now if you look at the points where this rank is less than m, this is a subvariety in X, or a sub-scheme in X. You see what I'm saying? For every point in X here, I have this S, which really locally is m vectors in E, and they can be dependent or not, linearly dependent or not. So now I'm describing here the points where these m vectors are dependent. Okay? That's a subvariety of X. So I call this here Z of S.
Blanco på S6 less than
Once more.
S6 less than +2.
So I see this should be the rank of Sx. The rank of Sx, sorry, yes. So Sx, S of x is a set of vectors, and they span a subspace, and now I look at the rank of that subspace. Okay. So you know the particular case where I have m equal to 1 and E is a line bundle. Right? Now, in that case, C of S in X is a divisor. It's codimension 1, it's a divisor. Right? And this is the divisor that you associate to L. This is the divisor that you associate to L. So the class, so this divisor moves in the linear equivalence class. Similarly, this cycle here moves in the rational equivalence class on X. And the class of, let me see, now I want to write it here. The Chern class. And now I need to get this correct here. Yeah, this is this C. And I want this here to be C R minus M plus 1. I think that's the right one. Yes, R minus M plus 1. So this here, this is the codimension of Z. So what I've described to you is how this Chern class, this particular Chern class of the vector bundle, gives you a geometric subvariety, I mean the geometric object, a subvariety of X. Well, the right way of saying this is more that it's a cycle, it's a class of a subvariety in X. And in general, you don't have lots of sections necessarily, but you can define Chern classes anyway, in a similar way. But this is how I think of Chern classes as giving me something geometric, The general case, the line bundle case that you know is this case, and for higher rank you get the different Chern classes this way. So that's so what this means is that for E you have Chern classes C0. This is just 1 because there's no this kind of stays this is really the name for the whole X. Now similarly Ci of E, I equal to 1 up to R. So well, at some point here, the codimension is going to be bigger, might be bigger than the dimension of X, so it stops. So it might not be that you have all these Chern classes for all these numbers here, just up to the dimension of the variety. Okay. So, and the main tool to compute, so one of the main tools to compute these Chern classes is the property of this kind of the splitting property, but the consequence of that is the way these Chern classes behave in exact sequences. So if you have a sequence of vector bundles A, B, C on X, and you write, so let me just take a baby example here. You have rank 2 there, rank 4 in the middle, and rank 2 in the other side. Then this guy here has Chern classes 1 and then C1 of A and C2 of A. As I explained, up to the rank. And similarly here, this B has Chern classes C1B up to C4B. And this guy here has 1 plus C1 of B, C, and C2 of C. And now I write this, I add them up. So these are then called total Chern classes. This is a strange thing because here, this kind of, as I said, there represents the whole variety, and this is a subvariety of codimension 1, this is subvariety of codimension 2, etc. In this picture, I'm not going to compute with them as subvarieties, I'm just going to work with them more formally. And the result is that if this sequence here is exact, then formally 1 plus the middle term here, this term here, is equal to the product of the two other ones. So this here is equal to the product of the two other ones. And if you think of this sequence here in the best possible situation, namely when this is a direct sum, that B is just a direct sum of the two other ones, then you see that this definition here of Chern classes fits nicely with this kind of product setting. And then you can prove that actually this generalizes to a product situation. So how should I read this? when I multiply out here, I get so this is identity in each dimension. So this is dimension 0, 1, or codimension 0, 1, 2, up to 4, and this is codimension 0, and similarly in this product. And so C1 of B is equal to C1 of A plus C1 of C, etc. So this can be used to compute. If you know 2 of them, you get the third by this computation. And how would I apply this in that situation? Well, in that situation here, the normal bundle fits into an exact sequence. If you take the tangent bundle of your surface, embed it into the tangent bundle of P4. Remember, our surface S lies in P4, and restrict that to the surface. Then the quotient is the normal bundle. So here you have an exact sequence of vector bundles on the surface. This one is of rank 2, this is one of rank 2, and this is of rank 4. And if you now write the Chern classes of these two, you get the Chern class of this one here. And so the Chern classes of this one here, in this right up there, is 1 minus K, the canonical divisor, is C1 of the tangent bundle. And then there is the C2 of the tangent bundle. This did not appear in our formulas before, but I'll come back to that. This guy here is, well, that's a tangent bundle on the projective space. And here, this is 1 plus 5h plus 10h squared. And I don't need to go further. It's really, you have 4 Chern classes here, but when you're restricted to your surface, only the first 2 survives. Because if you take C3 of this one, it should give you something of codimension 3 in the surface. That's nothing. So it doesn't survive. So you don't have to go further. And from these 2, one could then compute the Chern classes of the normal bundle. The final remark, the C2 here, this did not appear as I wrote it before. So that's because there is a completely different general statement saying that if I take C, so if I take K squared and C2 of the tangent bundle and add the 2, then I get 12 chi. It's a very general statement on invariance on a surface. But all of this is explained much better in the appendix. So now you know some of the things going into that. So this is very short and very sketchy. Chern classes is a very useful tool, and can be introduced quite formally. I wanted to give you here a hint of how this is really give you some subvarieties. It comes really from this kind of statements here. When you have a number of sections in a vector bundle, then they drop rank on a variety, and the class of that variety is representing a Chern class.
Are these sections chosen somehow generically? You can't just take one section and multiply it by sequence of different.
This here, yes. That's very important, you know, to make any sense here, because first of all, I'm saying that the vector bundle should have that many sections. I'm looking for a situation, I'm assuming a situation where you have lots and lots of sections, lots and lots of independent sections.
But they don't have to be linearly independent everywhere.
No, that's right. But whenever you choose m general sections, they will be dependent on in some subvariety. And that's exactly this C. So if you choose the more special, then the variety, well, then they will drop rank. They will become dependent in more than such a thing, in a bigger variety. Right?
This is the smallest.
This is the smallest it could be. This is the smallest it could be. So think about this situation here with the line bundle, right? You could have taken this 0 section. It's 0 everywhere, right? And you get the whole thing. But if you have a section which is not everywhere 0, you get a divisor. Similarly, if you have a rank 2 and you have 2 sections, if you have 2 sections, they could be both of them could be 0 and then it vanished everywhere. They could always be, so the one could be a proportional to the other one, and then they're always dependent and you get the divisor. Or in general, if they are independent somewhere, they're going to be dependent in, 2 of them will be dependent on a divisor, and 2 of them will be 0 in codimension 2. Yeah, this was lots, so there's a lot of things going into it. But this here, the way I defined it, is assuming that you have plenty of sections that are independent, generically. And they will always, this is very important also, they will always vanish, they will always drop rank in this codimension here. Unless it is the trivial bundle. If you take the trivial bundle, right, then you just take, then they are independent everywhere. And the Chern classes of the trivial bundle is therefore all 0. Okay? Other questions? Very good question. So then I move on to the second thing, the arithmetically Macaulay. So I did some of that really quickly, but let me do this properly a little bit more, in more detail. So I have my surface in P4, and H in S is a hyperplane section. Right? Then what I was saying is that if H, so it's also a curve in P3, in the hyperplane. If H is arithmetically, so ACM, arithmetically Macaulay, and this means now H I of the ideal sheaf of H twisted by K is equal to 0. So here I only need 1, in fact, for all K. And OH of H is non-special. That really means that H2 of HI of 1 is equal to 0. And if you think about non-special, this is a non-special divisor on this curve. Non-special divisor on this curve, this means that it has no h1, that this divisor has no h1. So for instance, if the degree is bigger than the degree of the canonical divisor, then it's non-special. So this can be computed, this can be checked just by the degree, sometimes, but not always. Anyway, this is that thing. If these two are the case, then S is ACM, which means that HI of IS of K is 0 for all K, and I equal to 1 and 2. And the one ingredient that I need for this, well, there are two ingredients, I should say. The one that I mentioned already last time, Severi's theorem, namely that H1 IS of 1 is equal to 0. So this is unless S is a Veronese surface. The other thing I need is Kodaira vanishing, which is more equally serious in a way. And what's that? Well, that is that H1 O of minus H so this is the same as H2 ideal sheaf of minus 1. Is 0. And actually, I could have put here a K there and a K there with K positive. So let me, before I go repeat the argument, so to speak, for this here, let me say a little bit about this Kodaira vanishing. Because there's some basic exact sequences that show up here all the time. And I'll put that in down here. The ideal sheaf of a hyperplane section, that's just O of minus H. Like that. So this is the ideal sheaf, or the defining sequence for the hyperplane section. And if you look at the cohomology here, well, S is a connected surface. So you have a 1 there. The hyperplane section is a connected curve. You have a 1 there. And there are no global sections over here, so this is 0. Right? So if this is this is certainly onto, so if you have 0 there, then you certainly have a 0 also there. Right? But you may not have a 0 there. Maybe you have something non-zero. maybe the surface H1 of O of S is non-zero. This is the key problem in this case, but still Kodaira vanishing says that you have a zero there. And the condition for this H is that this is an that we are going to use is that H is a very ample divisor. So if you do that for any divisor, it doesn't always work, you know. So, but this kind of thing, this kind of vanishing, you'll see in many disguises. But what we're going to use is that when H is very ample, then this is zero. Therefore, I can use also K times H for any positive K. I get still zero. Okay. So how did I apply this to get? Yeah.
You prove this.
This now I'm going to argue for this. I will prove this.
I think I don't. You don't need to assume the non-speciality of the curve.
You don't need to assume that. Okay. We'll see at this point where. Yeah. You may be right. Yes. So what I'm going to use all the time is, as I wrote up Monday, is the exact sequence where you multiply by the form defining H. This thing here. And so, whatever we have here for H0, we know that for H1, by assumption, you always have a zero. Right? Now, if you have one zero, if you have a zero also here, then you would automatically get a zero there. Right? Now, I could get a zero there by just taking k equal to 2, right? Then I do have a zero. If k equal to 2, then I get a zero there. And therefore, I get the zero here for all k bigger than 2. Put 1 there and then 2, then I put the 2 there and then 3, etc. For H1. Right? Now if I want to go the other direction, if I want to go to the negative ones, I have when I have a zero there, let me see, is there any trouble at all here? So for 2, if I have a k equal to 1 here, I get a 0, and then I get a 0 there, and then a 0 there. I have no linear forms in the ideal of H. So therefore, I get 0 there again, and then I can move backwards. And I can move backwards. So that takes care of H1. So it's the H2 where you say that is not necessary, right? So now for H2. So I have the 0 there. So if I have a 0 at one spot here and one of these two to be 0, then I'm through also, right? And here I can use the Kodaira vanishing to get one of these. Well, if I use the Kodaira vanishing to get a 0 there, I would get, because of this one, because of this one, if I have Kodaira but they are vanishing here. The 0 there, I would get the 0 for the previous one. And now we see, so for k equal to 1, for k equal to 1, I get let me see. You have a 0 there, and let me well, I would use, so if this is non-special, I have a 0 there for k bigger than or equal to 1. I have also a 0 there, right? And so therefore these two would be I got stuck there. Do you see why? But you claim that you don't need it.
Because on the H2 right there, the first map is always injective for all twisted.
The first,
Yeah,
this one is always injective.
Yes, and the second one is 0 for high.
For all higher, yes.
So it shouldn't change.
And why is this always injective? Because of this one here. Yes. Yes. This is always, because of this one here is completely right. So this is all gone. You have an exact sequence here. You have a 0 there, so it's injective from there to there. And so you have an injective map from H2 is of k minus 1 to is of k, and from this one to the next one, etc. But in the end, when k is big enough, you get a 0 here. So it must have been 0 all the time. Very good. Thank you. Okay. So this is useful for us because we take a surface, look at its hyperplane section. If the hyperplane section is arithmetically Comic-Cauley, then the original one is, the surface is also. And mind you, as I said, S is ACM, or C is ACM, if and only if SC is defined by, so, the maximum minors of a n by n plus 1 matrix of linear forms or of polynomial forms. You could put it differently, that you have A to B S or C, that you have a resolution of this ideal where A and B are free sheaves. This is a sum of line bundles, and that's another sum of line bundles. And this is like 1 to n, and this is 1 to n plus 1. And so here you have a matrix defining this map, and the maximal minus of that matrix is the ideal of the surface or the curve. That's what I'm saying by the slash here. You get it similar for the curve by just taking the restricting to a hyperplane. So therefore, with this, let's see what happens in degree 5.
Now we can write the degree in terms of AI and PI now.
Yeah. So yeah, we'll see now yeah, certainly the degree of the invariant, the degree of the entries in the matrix are certainly determined by these two. So, okay. Now, for d equal to 5, I have my surface S, and I look at the hyperplane section. So this is a curve in P3. So what kind of curves in P3 are there of degree 5? So the genus, which is what I used to call just pi, this is then either 0, 1, or 2. If you look at the Castelnuovo bound, there is a bound for the genus of a curve. Well, you don't have to go to all that far, you know, but anyway, there is a bound for the curve, and that's 2. If the genus is more than 2, if you have a genus 3 curve, you cannot put the genus 3 curve into P3. Well, if you try, it will lie in a plane if it has degree 5. So we have these 3 possibilities. Well, rational curves of degree 5, they are certainly very much projected from P5. And so the surface itself must be also projected. Since so this is actually out of the question here. Impossible. So I'm doing this a quick way. I could involve the double point formula, see what are the invariants of the other invariants here. But this is, as a rational curve, this is projected from P5, therefore the surface must also have been projected, and this is against the Severi theorem. So what about genus 1? Well, there I have to be a little bit more careful. Still, elliptic curve of degree 5. Elliptic curve of degree 5. If you look at the exact sequence, and look at the global sections, I know by the Severi's theorem I have 5 sections here in the middle. I certainly have a section there, and if I look at the degree 5 divisor on the elliptic curve, it has 5 sections by Riemann-Roch. 5 sections. An elliptic normal curve of degree 5 lives in P4. So I have 5 sections also there. So this elliptic curve is also somehow projected into P3. But in this case, well, if this is going to work out, I need to have a 1 over there. You see this by the exact sequence, right? For this to work out, I need to have at least a 1. And so this means that this is an irregular surface. It could have, a priori, it could have irregularity 2 or 3 also. But that's not the case. I will, actually the double point formula in this case implies that the k squared is equal to 6 chi, and this means that the H1 of O of S is bigger than -1. So I'm sorry, this is a bit too quick. If you compute the double point formula, you get a relation like this, and then you get that k squared is equal to 6 chi, then the q couldn't be bigger than 1. The q couldn't be bigger than 1. It would have been, if chi is negative here, then it's 8 chi and not 6 chi. Less than, or bigger than or equal to 6 chi. So it's a 1 there, and so I think I'll just write up here, S is an elliptic scroll. We'll actually come back to a construction of this later. This is going to be an elliptic scroll. And yeah, we'll see this in different ways. So it's actually a family of lines parameterized by an elliptic curve. And every section is then an elliptic curve. So that's the genus 1 case. What about the genus 2 case? Well, if genus is 2, then H is the hyperplane section is a genus 2 curve of degree 5. This is linearly normal in P3. It lives on the quadric, is a curve of type 2, 3 on the quadric. So a quadric is P1 cross P1, so you have this, the numbers here indicate how this curve intersects the two families of lines. And the genus is then given by the product of 2 minus 1 on this side and 3 minus 1 on this side. So more importantly here is that this curve is arithmetically Comte-Colli. This curve is arithmetically Comte-Colli. And the matrix have polynomials of these degrees. The matrix that defines this matrix that defines this is a 2 by 3 matrix with these linear forms and 2 quadratic forms. You see the minor here is the quadratic surface that it lives on. And then you have two more cubics to generate the ideal. And when this is the case there, then the surface is ACM by our argument with the same kind of matrix. So it just lifts. Okay. So the ACM curves, or the ACM surfaces, are easy. They come from ACM curves. And there are then essentially these two kinds.
S is always rational when pi is 2.
So he goes on, he asks, what is this surface? What is this surface? Is it always rational? So we shall certainly come back to that carefully, but this surface S so this is the equations, and he asks, is it rational? So let me just from the equations tell you why it is rational. And then afterwards I will give you a linear system. Just from the equations, see why it's rational. So here's a quadric. There is a quadric in the ideal. This quadric has rank 4. It's singular in P4, right? Because you have only 4 linear forms involved. So the 4 linear forms vanish at a point. Therefore it's singular at that point. And so the quadric, the surface lies inside a quadric, which is a cone over a smooth surface in P3. So I'm assuming that these are linearly independent, you see, right? So here's a cone point, and I have these 2 families of lines in the surface. Those give me 2 families, so let me write another one here, of planes. Right? So the surface lives inside here, so it will intersect all these planes. One family of planes in there are 2 families of planes, and they will intersect those 2 families in different degrees. So one family is given by giving the following way. If these 2 linear forms vanish, those 2 vanish on the plane, and then the surface on that plane is a restriction of the cubic defined by this minor here, right? Similarly, if I take these 2 linear forms, I get a plane, and that plane intersects the surface in the curve defined by the matrix I get by taking these 2 and these 2, those 2 columns, right? And I can move here in the pencil, so I really get all those. So this means in one family here I get cubic curves. What is the other family? The other family is where I go this way. So I take these 2 forms. That's a plane also. I define a plane. And in that plane the surface is the surface intersects along the conic defined by this one. Right? Because if all these 3 vanish, then the rank is 1. So therefore you get a conic in that other family. So the 2, 3 that I had downstairs for the curve now becomes really a 2, 3 in this quadric surface. Now conics and cubics, right? So on the other hand, both families are parameterized by a P1. So now you have a P1 family of conics. That's the rational surface. P1 family of conics. That's the rational surface. And the linear system is actually this one. So 4L minus 2E1 minus E2 minus. Let me see if I get it right. 7. Says minus 12. This is right? So what does this mean? I've blown up P2. I've blown up P2 in 8 points. So S to P2 are P1 up to P8, and you have E1 up to E8 over there. And then you have a line L, and the pullback of a line is this L upstairs. So this is the way I write this linear system. It comes from a linear system of quartic curves, the quartic curves in the plane that have one double point and 7 simple points. You compute the degree. It's 6. When you take the square, you get 16 minus 4 minus 1 minus 1, etc. minus 1. So that's 12 minus 7 is 5. And the genus of this curve, well, if it was smooth, it was, as a quartic has genus 3, has one double point, so it's genus 2. So those two are okay. Of course, how could this possibly how could this possibly be very ample? How can I really prove that this is a very ample linear system, right? So this is another thing that we'll look at next time, if we want to do it directly from here. But we'll also see next time how you can get this kind of linear system from this. Here we really have the surface. We have the equations directly. And there is enough room here to get to something smooth and nice. No problem. But to get the linear system, you can use what I will call, or what is called adjunction theory to get this in the end. But anyway, that's going to be the solution to that. Okay. So now, any questions to this? Yes?
Minus K over S is angry, or?
So minus K on this one, on this surface here, because you've blown up just 8 points. But we'll see later we blow up more than 9, even 10 points. And then minus K is nothing. Well, it's a nice canonical, it's a nice anticanonical divisor, but it's not a curve. There's no curve there. So that's where the trouble starts, when you blow up more than 9 points. But we'll see those things happening. Okay? But up to 8, it's not so bad. Okay? Any questions here? I wanted to really see here, this is important, the ACM construction. Whenever the curve is arithmetically Comic-Cauley, it lifts to a surface that is this way also. Okay? Now, I will go to this one here. Let's see if we can deal with that. So maybe if someone has a solution to this one. I don't see any quick way, so this is But how should we start on the problem? How should we start? So S I've blown up 3 points. So any linear system on this, if it's going to be embedded in P4 by some H, by some linear system, then this H must be of the form AL. So I'm using the same notation all the time here. The pullback of a line from the plane is small l. A times L minus B1 E1 minus B2 E2 minus B3 E3. That's the form. And now let's look at restrictions. Right? So we want to have an embedding into P4. And there must be some restrictions on A, B, and C. Well, first of all, A, B1 up to B3, these are integers, right? To start somewhere. The integers. More than that, is there some restrictions on these integers?
It should be positive.
Positive. They should all be positive. Because, well, if this is 0, I'm talking about, or negative, then I don't have any curve in the plane to start with. So this is certainly positive. And if any of these are negative, then the exceptional divisor becomes a fixed component. And then it's not a very ample system. And if any of these are 0, then I'm not talking about, then this map here will contract the curve and it's not an embedding. Will contract the exceptional divisor again. So all of these are positive. That's the first restriction. Of course, you see I talked about last time this, and I've talked about it today also, this restriction. But before we use that, let's look at the other restrictions that we have. So we have, there's a Severi theorem, right? The number of sections should be exactly 5, because we know this could not be the Veronese surface. Right? So this means, so H naught of H. And how do we compute that? Here we just 3 points. So these all give independent conditions. So we get here, how many curves are there of, how many forms are there of degree A? That's A plus 1 over 2. A plus 2 over 2, in fact. And then the number of conditions to have a BI multiple point is that all the partials up to BI vanish. So this is BI, B1 over 2, B2 over 2, and B3 over 2. Should be 5. Okay? So this is one relation. Start somewhere. Okay? And What about the genus? The genus of this curve, we could also express that. So 2 pi minus 2 is equal to h times h plus k. Remember, k is minus 3l plus e1 plus e2 plus e3. So this is A. I just multiply this here with the h plus k, and h plus k will have A minus 3 there. And then minus b1 times b1 minus 1. Like this. So you see, it's not, I mean, you have some of the same terms here. So you'd like maybe to use that a little bit, just to get some condition on the genus from the 5. So pi minus 1, I just divide by 2 here, then I get a minus 3 over 2 minus b1 over 2, b2 over 2, b3 over 2. And so if I subtract this here from that thing, what do I get? I get a plus 2 over 2 this guy here minus this one minus this one minus this one, and this one minus this one. And on the other side of the equality, I get 5 minus pi plus 1. And I think this here is a plus 3, a squared plus 3a plus 2 over 2, and then minus a squared minus 3a over 2. So this should be 3a plus 3a, 6a over 2 is 3a, and then plus 2 over 2. Is right? Do you agree with this here? So what do I get here? So pi 6 minus pi, I could put pi over on that side, and I get 6 minus 3a minus 1. Is that right? To pi. Does this, let's see, 6, I subtract, yes, right, huh? So pi is 5 minus 3a. Okay? Are you all happy with that? Well, why is this okay? Well, I have a connected surface I have a smooth surface actually. The hyperplane section is a smooth curve. And the smooth curve has a positive genus. Or 0. So this number here could not be negative, right? This is also non-negative, right? So then I have only, well, if A is positive and 5 minus 3 as A is positive, I have only two possibilities. A is equal to 0 or A is equal to 1. Well, A0 is not useful either, right? So A equal to 1 is the only possibility. But then when A is equal to 1, I'm talking about lines here. And lines, whatever conditions I impose on that, is not going to give you an embedding into P4. So not even using this thing here, I get to this. I hope I got all the numerics right here. But I mean, if this was a mistake somewhere, there is some more things. And certainly you get a very short list this way. And the point is that you can, point for me to give you this example is that there is some numerical data that you could put up, but there are some geometric restrictions on these numerical data. There's already here, and then next time here, and so on, and then the Severi theorem, you don't need much to really exclude the most possibilities. So this is a surface that cannot be. So maybe I will end by saying, so we'll certainly go through many more cases here, but so now that we've seen one surface that cannot be embedded, and I started out with the whole series by saying there are these certain restrictions. And in terms of classification, there is a finiteness that is very interesting. Now, this can be stated the following way: if S in P4 is a smooth surface of degree D that is not of general type. And not of general type means that the canonical divisor is not ample or not very positive. So this includes rational surfaces, ruled surfaces, abelian K3 surfaces, and elliptic surfaces. Of course, not necessarily minimal, meaning these surfaces may have been blown up in lots of points like this. In lots and lots of points. Still, if it is of this kind, then the degree is less than or equal to, I think the number is now 60. Degree is at most 60. And then you might worry, well, we've seen a few in degrees 3, 4, and 5. How far do we have examples? So known examples up to degree 15. Up to degree 15. So for rational surfaces, I think it still is degree 12, which is the maximal degree known. For non-minimal abelian, you have degree 15. So any non-general type surface of degree less than or bigger than 15 would be a big thing, and any new surface also less than degree 15 is important. Okay, and we've seen the first, and we'll see a little bit more of those between degree 5 and 15 in the next lectures. Okay, thank you.